Okay, this week we start with harmonically excited systems and STUF system subjected to a harmonic excitation, and we start with undamped system and continue, and finally at the end of the week we try to finish the system with viscous damping subjected to harmonic excitation. So first we will have an introduction to the force vibration and what is this type of problems, equation of motion, and we will extract the equation of motion when we have external force. We will extract the response of an undamped system under harmonic force, and we will study the beating phenomenon, which is related to the external force, and it will happen in the system under harmonic excitation. And finally, we will discuss the response of a damped system under harmonic force. So the force vibration means that we will have an external energy which is supplied to the system. This external energy can be supplied through external force or applied force, or it can be supplied by an imposed displacement excitation, which is called the base excitation or base displacement excitation. The applied force or displacement excitation can be in different forms. The first and maybe the simplest form is the harmonic excitation or harmonic response, which will cause the harmonic response. The second one is the excitation is non-harmonic, but it's periodic. And you will see in the next chapter that we will find the response for this type of excitation, which in this type of systems we can find the equivalent harmonics for a periodic excitation, and then using the method which is introduced in this section, we will solve the equation of motion. The third one is when the system subjected to a non-periodic excitation. For this type of problems, we will introduce some other methods such as Laplace and some numerical methods. And finally, the random excitation. And for this one, again, we will introduce the numerical methods, the for the random one, we will have the convolution integral, and we will discuss this one in the next chapters. Okay, so we will have 4 different types of loading, and start with the harmonic. The harmonic, as you know, can be in different forms. The exponential form, as you can see, F naught exponential I omega t plus v, which omega is the frequency of the excitation, F naught is the amplitude of the excitation, and phi is the angle phase. It can also be in different forms of cosine or sine harmonics. Again, F naught cosine omega t plus v, which F naught is the amplitude, omega is the frequency of excitation, and phi is the angle phase of the excitation. And also we can have the sine form of the external force. So to extract the equation of motion for a system, for a single degree of freedom system subjected to a external force like Ft, we can easily write the force equation similar to the previous chapter for a free vibration of STOF. Here we can use Newton's second law. If you write the force equation, for example, in this case, if you write the force equation in vertical direction, which is called x, you can write the force equation. We will have a force due to the spring. We have a force due to the damper. We have one external force Ft, and also we have the weight, but as I told you, because in this course and in vibrations, this weight will create some initial deflection in the spring. We can ignore the weight in the equation of motion, and also we neglect the initial deflection in the spring. So in the free body diagram, we only have three forces: one Ft, the external force; one the force of the spring, which is K times by X; and one force of this damper, which is C times by X dot. The direction of Kx and Cx dot are in the opposite direction of the motion, so they will have one negative sign. And the Ft, which is positive, because the direction of Ft is in a positive direction of the motion, so it will be positive. So the summation of the force is equal to Ft minus Kx minus Cx dot, and it must be equal to the mass times by the acceleration, which is mx double dot. By simplifying this equation, you can extract the equation of motion, which is written here, and it's mx double dot plus 6 dot plus kx. It must be equal to ft, which is the external force. As you can see, this is an ODE from order 2 with some non-homogeneous term. And now to solve this equation, we need to obtain the homogeneous response as well as the particular response. So the response for a system subjected to an external force is it includes two components. The first part is the homogeneous solution, and the second part is particular solution. And if you remember in week 1, as I explained, the homogeneous solution is called transient solution, and the particular solution is called the steady state response or steady state solution. So in this chapter, for a system under forced vibration, we will have one steady state response and one transient response. So if you plot the response for an underdamped system, if you remember that an underdamped system has a damping ratio or psi which is less than 1. So for this type of system, when we have viscous damping with damping ratio less than 1, if you plot the homogeneous response, it will something like this. As you can see here, this is the homogeneous response. And after a while, the amplitude of the response vanish and it will be 0, as you can see. But we will have in this chapter, we have an additional term, which is xpt, or the particular response, or steady state response. And as you can see, it has an harmonic of form, and of course this is a system subjected to a harmonic excitation. So you can see the response is again it has a harmonic form. And finally, the total response or the general response is equal to the homogeneous response plus the particular response. And as you can see, it's the summation of these two harmonics. And here you can see after a while, about here at after the period, let me use my pen. After this point, the response, the total response is almost xpt, because after this time, the period, after this time, if we call it tau, after this time, the homogeneous response is 0. So the total response after tau is equal to xpt. So here you can see that why we use these names for the xp and xh, or for the homogeneous and particular response. And you can see the reason that we use these names for the particular and homogeneous solution in vibrations, because the homogeneous solution after a while will be 0, and it will be called in vibration, it will be called the transient solution. But the particular solution will remain, and after tau, after this time, the total response is equal to the particular response, and so we call it the steady state response. Any questions so far? Is it clear? Okay. So we want to solve this equation for an undamped system. You know, when we deal with an undamped system, the damping coefficient is 0, or we don't have damping or x dot term into the equation. So the equation of motion is mx double dot plus kx is equal to ft, which here we assume that the system is subjected to an cosine or harmonic excitation, which is f naught cosine omega t. Omega is the frequency of excitation, and f naught is the amplitude of the excitation. Just please consider that this omega is different from the natural frequency omega n. So this is the frequency of the excitation, and omega n is the natural frequency of this system, and it will obtain from the homogeneous or from the free vibration response. So the response for this system, as you know, includes two parts. The first part is the homogeneous solution, and the second part is the particular solution. Here, this is the first part, the homogeneous solution, if we call it XH, and this part is the particular solution, which we call it XP, or the steady state response. So you can see, let me clear this. This is the XP, or the particular solution. So you know how to obtain XH, or the homogeneous response, and also you know how to obtain the particular response from the chapter 1, as I explained and I reviewed the ODEs. To obtain the homogeneous response, you need to form the characteristic equation. The characteristic equation for this equation is m alpha squared plus k, it's equal to 0. And then you can obtain the roots for the characteristic equation, which is plus minus I omega n. And then you know that the response for this system is C1 cosine omega nt plus C2 sine omega nt, which C1 is this term and C2 is this term. So C1 and C2 are obtained from the initial condition. And also we have one particular solution or particular response, because we have non-homogeneous term f naught cosine omega t. Here you can see that the non-homogeneous term is a cosine function. So the particular response for this non-homogeneous term is d naught cosine omega t plus d1 sine omega t, a combination of cosine and sine function with frequency of omega. Then you need to substitute the particular response into the equation here. I mean, you need to find the x double dot, the second derivative of d naught cosine omega t plus d1 sine omega t, and then substitute here instead of x double dot and x, and simplify. You will have two equations. One is the coefficient of cosine omega t in the right hand side and left hand side of the equation, and the second equation is the coefficient of sine omega t in the right and left hand side of the equation. And then you can solve these two equations and obtain d naught and d1, which this is d naught or d0, and d1 will be obtained 0, because as you can see here in the right hand side of the equation, the coefficient of sine omega t is 0, so it will be, and in the left hand side we don't have x dot, so easily we can conclude that the coefficient of sine is 0. So this is the particular solution and homogeneous solution in the general form, as you can see, as a function of the initial condition, which are x naught and v naught. X naught is the initial displacement at t is equal to 0, and v naught is the initial velocity at t is equal to 0. And omega n, here again, please pay attention that omega n is the natural frequency, and it's equal to a square root of k divided by m. But this omega is the frequency of excitation, is this omega, okay? And it will obtain from the particular solution. So this is the response of the system, the total response of an undamped system subjected to an cosine excitation with amplitude F naught. So now we want to discuss the effect of this external force and the effect of the frequency and amplitude on the response. For this purpose, we define the static deflection. A static deflection is delta st is equal to F naught, which is the amplitude of the excitation, divided by the stiffness of the system, which is K. And also we have the maximum amplitude of particular solution, which is F naught divided by K minus M omega squared. This is the amplitude of the particular solution, and you know, because it is multiplied by a cosine function, the maximum value of xp is its amplitude, because the cosine is between -1 and +1. So the maximum value of cosine is 1. So the maximum value of xpt is its amplitude, which is F naught divided by K minus M omega squared. So we call it x, which is the amplitude of the particular solution. And now we define a new parameter, which is called dynamic load amplitude or magnification factor. And it's the ratio of x, uppercase X, to the static deflection. And it's equal to 1. If you simplify this time, it will be equal to 1 divided by 1 minus the ratio of omega to the omega n squared. And this term, the ratio of omega to omega n, is called the frequency ratio. So now we can discuss the magnification factor, which is an important parameter in a dynamic system in terms of the frequency ratio. Any questions so far? Is it clear how to obtain the x, h, xp, and their constant coefficients? Okay. So if we plot the variation of the DLA or magnification factor with the frequency ratio, which, as I told you, this is the frequency ratio, the ratio of omega to omega n, which omega is the frequency of excitation and omega n is the natural frequency of the system. The response of the system can be identified to be of 3 types. The first type, or the first case, is when the frequency ratio is between 0 and 1, is less than 1 and more than 0. For this case, you can see that the harmonic response, if we call it xp, is in phase with the external force ft. You can see both of them have the same behavior, and we call it that xpt is in phase with the ft. But the second case, when the frequency ratio is more than 1, in this case, you can see that xpt is minus times by uppercase X, which is the amplitude, times by cosine omega t. And for this case, we say that xpt is pi radian out of phase with the external force. As you can see, at t is equal to 0, the force started from the positive value of F naught, but at the same time, the response starts from minus X. So minus uppercase X, of course, because uppercase X is the amplitude of the response. So in this case, we say that the response is pi radian out of phase with the external force. And finally, the last case, when the frequency ratio is equal to 1. In this case, when the frequency ratio is equal to 1, it means that the omega is equal to omega n, or the frequency of excitation is equal to the natural frequency of the system. And in this case, you can see that the magnification factor will go to infinity. Because if again, back to the previous slide here, the first slide, this term DLA, or the magnification factor, is equal to 1 divided by 1 minus frequency ratio squared. When this frequency ratio is equal to 1, so the denominator of this fraction is 0. So DLA, or the magnification factor, is equal to 1 divided by 0, and 1 divided by 0 is equal to infinity. So for this case, when frequency ratio is equal to 1 and omega is equal to omega n, so the magnification factor is infinity. As you can see, if you plot the response by increasing the time, the amplitude of the response is increased without any bound, and it will go to infinity. This phenomenon is called resonance, as you definitely know. So when the frequency of the excitation is equal to the natural frequency of the system, we can see this phenomenon, and it's called resonance. And here, by using the equation of motion and the mathematical equation, you can see this behavior in your physical system. So if you plot the response for the total response, of course, of the system, this is the total response, is the summation of the homogeneous response, as you can see, and the particular response. Of course, we rewrite this equation as a function of delta st, the static deflection, and the frequency ratio, okay, for the case when the frequency ratio is less than 1. Here you can see, for this case, when the frequency ratio is less than 1, we have one long period, which is 2 pi divided by omega, which omega is the frequency of the excitation. And also we have a small period, which is 2 pi divided by omega n, which omega n is the natural frequency of this of the system. And here you know that omega n is more than omega according to this term, because the frequency ratio is less than 1, and omega n is more than omega, so the period for the omega is more than period related the associated period for omega n, or the period of the system is less than the period of the excitation. So this is the response in case 1, and as you can see, the response is vibrating about another curve, which this curve has another period and a different frequency. And for the case when omega to the omega n, or the frequency ratio, is more than 1, in this case omega is more than omega n, or the frequency of the excitation is more than the frequency of natural frequency of the system. And we can conclude, when omega is more than omega n, the period of the excitation is less than the natural period of the system. As you can see, this is the small period, it's 2 pi divided by omega, and this is the period of the excitation, and this large period is 2 pi divided by omega n, which is the period of the system. And again, you can see that we have one vibrating about another curve, and this curve is in fact the curve with the period of the system, and the period of a vibration in fact is equal to the period of the excitation. So this is the second case when the frequency ratio is more than 1. Any questions so far? In fact, we are investigating the behavior of the system for different value of the frequency of excitation and amplitude of the excitation. No question? The next concept is the beating phenomenon. If the forcing frequency is close to the natural frequency of the system, we will have a phenomenon known as beating. Here we can assume that this is the response for a zero initial condition when x naught and v naught are zero. So the total response is equal to f naught divided by m times by omega n squared, which omega n is the natural frequency, minus omega squared, which omega is the frequency of the excitation, multiplied by cosine omega t minus cosine omega nt, which this term is the particular response, and cosine omega nt is the homogeneous response. So in the previous slides, if you refer to the previous slides, the form of xt as a function of x naught and v naught, if you substitute x naught is 0 and v naught is 0 as well, you can extract this response for your system. And here you can see we can use the trigonometry relation and extract this equation for the xt. As you can see, we can convert the cosine omega t minus cosine omega nt is equal to 2 times by sine omega plus omega n divided by 2 times by t, multiplied by sine omega minus omega n divided by 2 times by t. So in fact, we are using the trigonometry relations and convert it from cosine uh, summation into the multiply two sine function, as you can see. And now we know that omega is close to omega n, but it's not equal. So we can define a new parameter, epsilon. If we assume that omega n minus omega is equal to 2 times by epsilon, which epsilon is a very small parameter, and because we know that omega n is approximately equal to omega, so we assume that the difference between omega and omega n is 2 times by epsilon. Now we can substitute here for omega minus omega n, we can substitute 2 times by epsilon, and here omega plus omega n as well, we can substitute and simplify this term. And finally we can extract the response in this form. As you can see, xt is equal to, instead of omega n minus omega, we can substitute 2 times by epsilon, and omega plus omega n, you can substitute, for example, instead of omega n, you can substitute 2 times by epsilon plus omega, because from this term you can conclude that omega n is equal to 2 times by epsilon plus omega. So if you substitute, for example, here, substitute instead of omega n, you substitute this term, you will have omega plus 2 epsilon plus omega. So it will be 2 epsilon plus 2 omega divided by 2. And then you can simplify this term, and it will be omega plus epsilon. And then you can expand these functions and extract this form for the xt. And you can see the response is a function of sine harmonic with frequency epsilon, which you know that epsilon is a very small parameter, so it's a very small frequency, multiplied by sine omega t. But this time the frequency is omega, and this is the frequency of the excitation, and it's close to the natural frequency of the system. So we can define a period of beating, which is called tau sub b, this term, and it's equal to 2 pi divided by 2 epsilon, which 2 epsilon, as I told you, is the frequency of the beating, and it's equal to the difference between the frequency of excitation and the natural frequency. And also we have the omega b, which is the beating frequency, and it's equal to 2 times by epsilon. So the beating frequency is equal to the difference between the natural frequency and the frequency of the excitation. This time, if you plot the response for this case, the xt, let me clear these lines. Here you can see, if you plot the response, you will have one sine omega t curve and one sine epsilon t. The sine omega t is this bold line, the black bold line, and sine epsilon t is dashed line, as you can see. And also it's clear that one sine omega t curve will go through several cycles because omega is more than epsilon, while the sine epsilon t wave goes through a single cycle. Here you can see the period of epsilon t is this distance, 2 pi divided by epsilon, but the period for the sine omega t is this length, and it's equal to 2 pi divided by omega. Okay, so this phenomenon is called the beating, and sometimes you can see this phenomenon when the frequency of the excitation is close to the frequency of the system, and you can see that here this is the response. As you can see, the amplitude will increase, amplitude of the response till here, again it will decrease, and again at this point it start to increase, and this phenomenon will be repeated after 2 pi divided by epsilon, and epsilon is the difference of the frequency of the excitation and the natural frequency of the system divided by 2. So this is the beating phenomenon. Any question? Clear? Okay. Okay, we continue with one example. A weight of 50 Newton is suspended from a spring of stiffness 4,000 Newton per meter and is subjected to a harmonic force of amplitude 60 Newton and frequency 6 Hertz. Find the extension of the spring due to the suspended weight, due to this 50 Newton weight. Part B, the static displacement of the spring due to the maximum applied force, or in fact we want to obtain the static deflection. And part C, the amplitude of force motion of the weight. So part A, easily we can obtain the extension of the spring due to the suspended weight. We have a 50 Newton weight with which is attached to a spring with a stiffness 4,000. So easily delta, or the X, is equal to F divided by K. F is 50 Newton and K is 4,000. So this is the part A. For part B, we need to obtain the static deflection. The static deflection is equal to the amplitude of the external force. The amplitude of the force is 60 Newton here, divided by the stiffness of the spring, which is K, and it's equal to 4,000. So this is the static deflection. And part C, we need to obtain the X, uppercase X, or the amplitude of the force motion of the system. As you know, the amplitude of the force motion is equal to the amplitude of the particular response, and it's equal to uppercase X. So we need to obtain the natural frequency. To find the frequency ratio, the natural frequency is equal to square root of K divided by M. The frequency of excitation is 6 Hertz. We need to convert it into radian per second. So we multiply by 2 pi, and it's equal to 12 pi radian per second. Now we can find the frequency ratio, which is equal to omega divided by omega n, and we can substitute to find X, uppercase X, and it's equal to delta st multiplied by the absolute. This is the absolute of this term, 1 divided by 1 minus frequency ratio squared, and you can substitute omega, omega n, and delta st from previous part and obtain the X. Clear? No questions? Okay. Okay, next example, we have a spring mass system with M is equal to 10 kilogram. This is the mass of the system. And the stiffness is 5,000 Newton per meter, is subjected to a harmonic force of amplitude 250 Newton and frequency omega. If the maximum amplitude of the mass is observed to be 100 millimeter, find the value of omega. So this time we have the x, the uppercase x, or the amplitude of the particular solution. And this time we need to obtain the omega, or the frequency of the excitation. So the first step, we need to obtain the natural frequency, which is equal to a square root of k divided by m. And also we can obtain the static deflection. It's equal to the amplitude of the excitation force, which is 250 here, divided by the stiffness, which is 5,000 Newton per meter here. So we have delta ST, we have omega n. Also, we have this x, which is 100 millimeter. It should convert into the meter, which is equal to 0.1, is equal to the static deflection multiplied by the absolute of this term, which this term is a function of frequency ratio, and we have one unknown omega. This time we need to solve this equation for omega, and if you solve and simplify this equation, you can conclude that the frequency of the excitation is 15.8 radian per second. Okay, so the required equation is similar to the previous example, but this time the unknown position changed, and instead of the amplitude of the response, we need to find the frequency of the excitation. Okay, any question? If you don't have any question, we can wrap up this session. Okay, thank you for your attention, and we continue on Wednesday. Thank you and have a good day. Bye.